All right, so we're going to look at graphing various monomials and using transformations. But then the main thing is we're trying to do is graph polynomials. So I know if I want to do a graph, then I could do a quick 3 points. So I know if it's y equals x, for instance, I might use, make sure I've got that. I might use y equals or 0, 0, 1, 1, and negative 1, negative 1. And I know that I get a straight line. So I'm not going to overdo this because we're a little short in time. We can talk about it a little more fully if you want to tomorrow. But I know if I want to graph y equals x to the third, I'm going to skip a little bit. That I'm also, make sure you're taking notes because, guys, you get yourself in trouble when you don't have notes that remind you of the things that we've gone over. And then you also don't have anything to go by if you get stuck on the homework. And that's kind of the point, right? So the problem is, how does this graph differ from this graph? Well, for instance, I know that 2, 2, because they've both got 0, 0, 1, 1, and negative 1, negative 1. But if you actually plotted more points, this graph would, of course, have, not where I put that, and I'm going to have to go big dot theorem a little bit. That would have 2, 2 on it. But like this graph would have 2, 8 on it. Are you with me? Now, another difference, I'm going to just estimate where this goes. Another difference on this graph is that if I did plugged in 1/2, this graph would have 1/2, 1/2. But this graph would have 1/2, 1/8. So the effect is that outside the x equals 1 and negative 1, the graph has to be a little bit steeper. But between the 1 and negative 1, the graph is going to be a little bit flatter. So you're going to get the effect of having a curve there. Okay? Well, the same could be true if I look at y equals x to the 5th. You could still say, well, I'm going to have 0, 0, 1, 1, and negative 1, negative 1. But this time, I would have 2, 32. So the outside edges are going to be even steeper. But the inside, I would have 1/2, 1/32. So the inside's going to be even flatter because the values between 1 and negative 1 are going to be smaller. So what happens is that, and I'm not perfect, and this is kind of the point of what we're doing right now. For you to know that that curve through the middle gets more significant, so you're going to see more of a flattening in the middle. And instead of the outside edges kind of doing this, the outside edges kind of pull in because they get taller. Okay? But the big deal is that y equals x to any odd power is going to be similar to y equals x to the third forevermore. Like I know y equals x to the 11th is going to be similar to y equals x to the third, but y equals x to the 11th is going to be even taller on the outside edges and even flatter through the middle. That's the way it's going to look. It's going to look more severe kind of in the middle. So that means if I were to say, hey, let's graph this one and let's make it quick, your reader is not going to be able to tell whether you're graphing y equals x minus 5th to the 11th plus 1, or whether maybe you're graphing y equals x minus 5th to the 7th plus 1. But that's okay. You just need a basic image and move forward. So I know the parent function here is y equals x to the 11th. I know y equals x to the 11th looks very, very similar to y equals x to the third. I'm using your is similar to squiggle from geometry. So if y equals x to the third I know looks like this, then what am I going to do with that graph? Like what transformations? Right 5, up 1? All right, so right 1, 2, 3, 4, 5, up 1. And so I know it's still going to be right 1, up 1, left 1, down 1. So I know what 3 basic points to plot. And then if it's y equals x to the 11th, I know that I need to kind of make the outside edges look steep and the middle part look kind of really flat. But guys, I can't graph it well enough by hand to let you know if it's a transformation of y equals x to the 11th or y equals x to the 19th or y equals x to the 5th. But I just need a good enough graph. Because think about it. What if I now said, are there any points of inflection? Is the graph monotonic? What's the range of the function? You can answer all of those kinds of questions with an imperfect graph. It's reasonable, it's good enough, it's not absolutely precise, but it's accurate. Are you with me on what I'm saying? So that's what I'm wanting you to get to. So the same is true on y equals x squared, y equals x to the 4th, and y equals x to the 6th. 0 squared is 0, 1 squared is 1, negative 1 squared is 1. But 0 to the 4th is 0, 1 to the 4th, and negative 1 to the 4th are both 1. All right, the same is true here. 0 to the 6th is 0. 1 to the 6th is 1. Negative 1 to the 6th is 1. So they all three have the exact same starter points. The same thing is going to be true, though. On this one, I would have 2, 4. On this one, I would have 2, 16. On this one, I would have 2 to the 64th. So the outside edges are going to kind of go from here to here to here. Are you with me? And that also causes the bottom to go from kind of almost a V shape, not quite, to being more flat and back up. You with me? But that's the only thing you can do. So the point is, guys, not can you draw y equals x to the 4th so well that I can tell that it's y equals x to the 4th, but do you know that y equals x to the 4th basically looks like y equals x squared? That's what the point is. We can't do a great job. We just have to kind of do our best. So you're going to see right now that my y equals x to the 6th is basically going to look at my y equals x to the 4th because I'm human. So without graphing more or plotting more specific points, nobody can really tell which one it is, but they could tell it's a y equals x to an even power. They might not know what even power, but they'll know it's one of those. Are you with me? And we know y equals x to evens equal, not are equal to, but they look similar in shape to y equals x squared. They're a little more significant, flatter bottoms, steeper edges, but they all kind of look the same. All right? So what if I said, let's graph this function? Well, what's the parent function? All right? So if the parent is y equals x to the 16th, you know that we're going to graph something that looks like y equals x squared. So transform y equals x to the 16th just like you transform y equals x squared. So what are some things that you would do to y equals x squared if that's what it were? Upside down, move it down 1. So you would go out 1, down 4. The a value is 4. It's still the same thing. So we're going to move it down 1. It's still going to be out 1, down 1, 2, 3, 4. So it's got the exact same first 3 points as y equals x squared. And I'm going to try to make it not look like quite so parabola-like. So I kind of make it flatter on the top to where the peak is a little bit less pointy and a little bit flatter. Those are really good mathematical adjectives I'm using there. But, I mean, it basically looks like a transformation of y equals x squared. Are you okay? That's my point. That's all I want to say. All right? So we're more focused on, well, what about polynomials? What if it's not just y equals x to the 4th? What if it's y equals x to the 4th plus x to the 3rd minus 27x squared plus 2x plus 1? How do you graph those? You've seen all this. This is easy and fun. All right? So, and I'll post this if you need me to. But remember, if you have a positive leading coefficient for one of these equations, what's that tell you about the graph? What's up? The right end is going to point up, yeah. So this is going to tell you that the right end is up. If you have a negative leading coefficient, then it tells you that the right end points right to the right and down, right? Okay, so we have to make sure that we know how to differentiate our roots. So do you know a single root just cuts through the x-axis? So that's going to be my buzzword. So it might be that the graph goes up through the single root or down through the single root. It just cuts straight through, just like a line would cut straight through the x-axis. Now, what do double roots do? All right, so my word for that is double roots kiss the x-axis. So a double root kisses the x-axis. So the graph might come down, kiss, and go back up. Or the graph might go up, kiss, and go back down, right? So those look like parabolas because it's x squareds or x minus 5 squareds or whatever it is. So then a triple root is going to slide. A triple root slides through the x-axis. So guys, on this one you might be a little less familiar, but it's going to look like the same thing with how y equals x cubed touches the x-axis. I'm going to overemphasize. So it's going to go up, slide right, and go on up. Or it's going to go down, slide right, and go on down. So that's what I mean by slide. Okay? So if we can't see the roots, we're going to have to factor. So you'll have some of that where you factor first, then name the roots. I'll show you. If you wanted the y-intercept, you would evaluate p of 0. I usually don't get hung up on that. Okay? So if you want to find the local maxes and mins, or the points of inflection, you got to take calculus. So that means you get to be a little wild and crazy this year. You can graph with abandon for one more year, and then you got to get more focused. So let me do a couple of these right now. And I tell you what, I will do some of the other ones. Maybe I'll do a little video at the end if you all want to go back and look at how to do some of the factored ones. But let's, for instance, skip to h of x because it's more complicated than the first two, just so you see a variety. So on this one, can you count the degree as 1, 2, 3, 4, 5? Can you see where I'm getting the degree from factored form? Okay. Can you see that my leading coefficient is 1/3 times this 2? If I were to multiply everything out at the beginning, my leading term would be 2/3 x to the 5th power if I did multiply it all out. Okay? So now I know that the right end is up because the leading coefficient's positive. But what if your degree is odd? What's my left end do? Left end's going to be opposite the right end. So when the degree's odd, the ends are opposite. When the degree is even, the ends are the same. Are you with me on that? So I know, for instance, that the right end points up, and now I know the left end points down. So I've discussed end behavior. So if I ask you to find the roots or the x-intercepts or the solutions or the zeros, whatever you like to call them, are you saying that 1/3 x squared as a factor is giving me 0 as a double root? I'm assuming that this should be pretty familiar. Are you saying that x plus 1 squared as a factor gives me -1 as a double root? Are you okay? Are you saying that 2x minus 3 as a factor gives me 3/2 as a single root? All right, so guys, if I don't label it, the default is that it's a single. If it's a double or a triple, then I'll label it. Could you have a quadruple root? Yes, in calculus. We don't go above single, double, triple in precalculus, okay? Because you need more stuff to know how to deal with those, and that's calculus. Yeah? I see that if I multiplied out the 1/3 x squared times x squared, that would be 1/3 x to the 4th, times 2x would be 2/3 x to the 5th. 2/3 is the leading coefficient, 5 is the degree.